Bismillah ar-Rahman ar-Rahim. We have a sum over positive n of 1 minus 2n minus 1, the inverse cotangent of 2n minus 1. The first step is to write down the inverse cotangent function in terms of the inverse tangent function. The inverse tangent of 1 over 2n minus 1 is integral x from 0 to 1 over 2n minus 1, 1 over 1 plus x squared. We can write down this one here as integral x from 0 to 1 over 2n minus 1, 1 plus x squared over 1 plus x squared. This integral is equal to 1 over 2n minus 1. To get 1, we multiply by 2n minus 1. The summand is 2n minus 1. Between brackets, we have this integral minus that one. They can be combined as the integral x from 0 to 1 over 2n minus 1, x squared over 1 plus x squared. Do the change of variables, y equal to 2n minus 1 x. When x is 0, y is 0. When x is 1 over 2n minus 1, y is 1. 2n minus 1 dx is dy. X squared is y squared over 2n minus 1 squared. The sum of interest is sum n from 1 to infinity, integral y from 0 to 1, y squared over y squared plus 2n minus 1 squared. We have this previous result. Summation n from 1 to infinity, cosine eta n, where eta is between 0 and 1, over n squared plus p squared, which is a non-zero real number, is minus 1 over 2p squared plus pi over 2, the hyperbolic cosine of b times pi minus eta over b times the hyperbolic sine of b pi. If eta is equal to 0, cosine eta n is equal to 1. This term becomes the hyperbolic cosine of b pi. If eta is equal to pi, we have cosine pi n, which is minus 1 to the power n. In the numerator, we have the hyperbolic cosine of 0, which is 1. Subtract this sum from this one. We get that summation n from 1 to infinity, 1 minus 1 to the power n over n squared plus p squared. The numerator is 0 when n is even, and is equal to 2 when n is odd. This sum is n from 1 to infinity, 2 over 2n minus 1 squared plus p squared. When we subtract, these two terms go away. In the denominator, we have b, the hyperbolic sine of b pi. In the numerator, we get the hyperbolic cosine of b pi minus 1. If theta is equal to b pi, this ratio here is e to the theta plus e to the minus theta over 2 minus 1 over e to the theta minus e to the minus theta over 2. This is e to the theta plus e to the minus theta minus 2 over e to the theta minus e to the minus theta. In the numerator, we have e to the theta over 2 minus e to the minus theta over 2, all squared. In the denominator, we can think of this as the difference between two squares. We have e to the theta over 2 minus e to the minus theta over 2 times e to the theta over 2 plus e to the minus theta over 2. Simplifying and dividing the numerator and denominator by 2, we get the hyperbolic sine of theta over 2 over the hyperbolic cosine of theta over 2. That's the hyperbolic tangent of theta over 2. The sum of interest is equal to this integration here. Let's interchange the order of summation and integration. We have integral y from 0 to 1, y squared, summation over positive integer n of 1 over y squared plus 2n minus 1 squared. Based on this result here, the sum is equal to pi over 4y, the hyperbolic tangent of pi y over 2. Y squared over y is y. We can take pi over 4 outside the integral. The hyperbolic tangent of theta is e to the theta minus e to the minus theta over e to the theta plus e to the minus theta. We can write the numerator with a plus sign, then subtract 2 e to the minus theta. This is 1 minus 2 e to the minus theta over e to the theta plus e to the minus theta. Multiplying upstairs and downstairs by e to the minus theta, the hyperbolic tangent of theta is 1 minus 2 e to the minus 2 theta over 1 plus e to the minus 2 theta. The integral y from 0 to 1 of y is 1/2 times pi over 4, that's pi over 8. Then we have minus pi over 2, integral y from 0 to 1, y, e to the minus pi y. We can write 1 over 1 plus e to the minus pi y as summation j from 0 to infinity, e to the minus pi y to the power j. Interchanging the order of integration and summation, this is pi over 8 minus pi over 2, summation j from 0 to infinity, minus 1 to the j, integral y from 0 to 1 of y, e to the minus pi y times 1 plus j. This integral is equal to minus 1 over pi times 1 plus j, integral y from 0 to 1, y e to the minus pi y times 1 plus j. This is minus e to the minus pi times 1 plus j over pi times 1 plus j, plus 1 over pi times 1 plus j, integral from 0 to 1, e to the minus pi y 1 plus j. Doing the integration here, this part becomes minus 1 over pi squared, 1 plus j squared, e to the minus pi, 1 plus j, minus 1. Combining these two terms, downstairs we get pi squared, 1 plus j squared. Upstairs we have 1 minus e to the minus pi, 1 plus j, minus pi, 1 plus j, e to the minus pi, 1 plus j. We have the sum of this quantity over non-negative integer j. This minus sign with minus 1 to the j is minus 1 to the j plus 1. So this minus sign becomes a plus sign. Then we can replace j by j minus 1. Every j plus 1 here will become j, and the sum now starts from 1 rather than from 0. Summation j from 1 to infinity minus 1 to the j over j squared is equal to minus summation j from 1 to infinity minus 1 to the j minus 1 over j squared. This sum is zeta of 2 minus 2 times 1/4 of zeta of 2. Zeta of 2 is pi squared over 6. these two terms give pi over 12. We also have summation g from 1 to infinity, minus 1 to the g plus 1, e to the minus pi to the power g over g. This is multiplied by pi over 2 pi, that's 1 over 2. This summation is the natural logarithm of 1 plus e to the minus pi. When the magnitude of z is less than 1, the dilogarithm of z is summation over positive integer g of z to the g over g squared. To account for this term, we have minus 1 over 2 pi, summation g from 1 to infinity, minus e to the minus pi, all to the power g divided by g squared. And this is minus 1 over 2 pi, the dilogarithm of minus e to the minus pi. Summation n from 1 to infinity of 1 minus 2n minus 1, the inverse cotangent of 2n minus 1 is pi over 12 plus 1 half ln 1 plus e to the minus pi, minus 1 over 2 pi, the dilogarithm of minus e to the minus pi. The second series is summation n from 1 to infinity, 2n choose n times minus 1 to the n over 4 to the n, digamma n+2 over 4 minus digamma n over 4. Let's call this summation omega. When the real part of alpha is greater than minus 1, the integral x from 0 to 1 x to the alpha over 1 plus x can be written as integral x from 0 to 1 x to the alpha 1 over 1 plus x is summation g from 0 to infinity minus x to the power g. If we integrate term by term, we have summation g from 0 to infinity minus 1 to the g integral x from 0 to 1 x to the power alpha plus g. This integral is 1 over alpha plus g plus 1. We can write down the summand as the difference between two terms. In the first one, we replace g by 2g. In the second one, we replace g by 2g plus 1. Multiply numerator and denominator by 1 half. Add and subtract 1 half over g plus 1. Digamma of z is equal to minus small gamma, Euler-Mascheroni constant, plus summation g from 0 to infinity, 1 over g plus 1 minus 1 over g plus z. The sum of this difference here is equal to 1 half digamma of alpha over 2 plus 1 plus small gamma. The sum applied to this bracket here gives 1 half digamma of alpha plus 1 over 2 plus small gamma. This integral is 1 half digamma of alpha over 2 plus 1 minus digamma alpha over 2 plus 1 half. If we choose alpha to be equal to n over 2 minus 1, so alpha over 2 is n over 4 minus 1 half. If we add 1 half, we get digamma of n over 4. If we add 1, we get digamma of n over 4 plus 1 half. This difference, which is here, is equal to 2 times the integral x from 0 to 1, x to the power n over 2 minus 1 divided by 1 plus x. The sum of interest, omega, is written now in terms of this integral. Interchanging the order of integration and summation, omega is 2 integral x from 0 to 1 over x times 1 plus x, summation n from 1 to infinity, minus 1 to the n times n over 4 to the n times the binomial coefficient 2n choose n. Then we have x to the n over 2. We can use the expansion of 1 minus x to the minus half when the magnitude of x is less than 1. This is the sum over non-negative integer n of 2n choose n, x to the n over 4 to the n. If we replace x by minus x, we get that 1 plus x to the minus 1 half is summation n from 0 to infinity 2n choose n minus 1 to the n, x to the n over 4 to the n. Differentiating both sides with respect to x, inside the sum, this x to the n becomes n x to the n minus 1. So we can start with n equal to 1. The derivative of this part with respect to x is minus half 1 plus x to the minus 3 over 2. Omega depends on this summation, summation n from 1 to infinity, 2n choose n, minus 1 to the n, n. Then we have x to the n over 2, all divided by 4 to the n. If we multiply both sides here by x, we get x to the n. On the right-hand side, we get minus x over 2, 1 plus x to the minus 3 over 2. To get this sum here, we replace x by x to the 1 half. So omega is equal to 2 integral x from 0 to 1, 1 over x times 1 plus x, minus the square root of x over 2 times 1 plus the square root of x to the power minus 3 over 2. Omega is equal to minus 1 times integral x from 0 to 1, square root x over x times 1 plus x times 1 plus the square root of x to the power 3 over 2. Use the substitution y equal to the square root of x. Square root of x becomes y. This x and that one become y squared. Dx is 2y dy. After simplifying, omega is minus 2 integral y from 0 to 1, 1 over 1 plus y squared times 1 plus y to the power 3 over 2. Let's use another substitution. T equal to 1 plus y to the power 1 half, which means that y is t squared minus 1. When y is 0, t is 1. When y is 1, t is the square root of 2. dy is 2t dt. This term becomes t cubed. This one becomes 1 plus the square of t squared minus 1. Omega is minus 4 integral t from 1 to the square root of 2, 1 over t squared. When we expand this, we get t to the power 4 minus 2t squared plus 2. if we do partial fractions, we can write 1 over t squared, t to the 4 minus 2 t squared plus 2 as 1 over t squared minus t squared minus 2 over 2 times t to the 4 minus 2 t squared plus 2. The antiderivative of t to the minus 2 is minus t to the minus 1. Using the limits of integration and multiplying by this minus 2, we get minus 2 plus the square root of 2. Then we have plus 2, integral t from 1 to the square root of 2 of t squared minus 2 over t to the 4 minus 2 t squared plus 2. We do partial fractions again, exploiting the fact that this denominator can be written as the product of these two quadratics. We get standard integrals that can be written in terms of the natural logarithm and inverse tangent functions. When we use the limits of integration, this part is 0. Our final result involves this part here, minus 2 plus the square root of 2, minus this part involving the inverse tangent function.